today I'm going to be talking about this framework called deck.gl. We recently open sourced this end of last year, and we released a new version, major version, like early this year. First, a little bit more information around our team. So we have 3 groups. We're divided into 3 different areas. One is called Business Insights. Main goal of this is, to visualize and analyze like data around our business, trips, financial data, et cetera, more related to abstract data visualization. And we're supporting all of the operations happening at Uber. So like, in every one of the 450 cities, we have CT teams that are basically trying to build strategies around their cities. And then the second area is advanced analytics. So we're building tools that have a narrower set of customers, but they're like power users and more kind of like advanced users. And so for that, we do work around experimentation, A/B testing, more around geospatial visualization, and then finally, more work around machine learning, so visualization. So it's a lot of like machine learning visualization to inspect and debug machine learning models. Finally, the third team arose with our collaboration with the ATG, the Advanced Technology Group. So they're doing some of the self-driving car stuff. And with that, the main skill set of that group is around computer graphics. As you can probably imagine, like a video game type of visualization. So areas are dashboarding, mapping, and frameworks. So cool, let's get into deck.gl. What is deck.gl? deck.gl is a large-scale WebGL-powered data visualization library. As you can think about the business, like we have billions of GPS points being going through our platform on a daily basis, and because of this, we have like a lot of interesting challenges that arise through like building data dense visualizations and having high performance visualizations because of this. And so we started crafting our own in-house kind of tool to visualize this data. Some of the principles behind it, high level, if you go to deck.gl, you get to see the framework. You can browse through the documentation gallery, etc. I won't go through that. This is very public facing and you can access this information. But some of the principles behind it, the first one was high performance GPU computing. So I think that deck.gl has, does something really well and then relies on other libraries to complement some of its features. In this case, for example, you get to see that, we use WebGL and the WebGL canvas to do this rendering, but we also partner with, for example, in this case, Mapbox for the base maps. And we do a lot of work related to like camera, kind of like synchronization between these 2 libraries so that like whatever you render is seamless between these 2 things. It also uses React. So it has, this sort of like React interface that makes it easy for you to use with those frameworks. The second point is this instancing and layering paradigm. So probably the easiest way, who here used D3 in the past? Okay, so in D3 you have this concept of instancing, and when probably it's not called instancing, but you have a selection, right, and of circles, and then you pass in an array of data objects, right? And then what you do next is you instance each circle with this data information. So you have a one-to-one mapping between the data objects in the array and the circles that you have, but then you slightly tweak each circle's attribute, color, radius, etc., based on the data or the properties of the data, right? So coincidentally, WebGL2 has this feature called instancing, where you can very cheaply and easily create a geometric primitive, like a cone or a sphere or whatever, and then you can clone it multiple times, and you can tweak it. So following the very same principles that D3 has and that InfoVis has, we follow this kind of same kind of philosophy. And then the layering paradigm comes directly from the geospatial stuff, right? So, maps have multiple layers. You have, land and water. You have street segments, routes. You have labels, et cetera, right? And all of those can be thought of as layers. Here, what we provide is a set of like a dozen of core layers, and then you can have, your own custom layers, and we'll go through that. But here, there's an example of 4 different layers. So you have on the top left a scatter plot layer, which is dots. On the top right, a way of aggregating data through hexagons, like hex binning. So that's done on the client side. And we're actually looking at like more GPU approaches to do that on the GPU as well. On the bottom left, we have a grid layer, which aggregates data by like equal area square. And then finally, on the bottom right, you have like an arc layer that connects, points that could be pickups and drop-offs or whatever other type of point that you want to connect. Finally, as I mentioned before, the layers don't only render data, but they also can perform operations on data. So in this case, for example, we have aggregation on data, filtering on data. In this specific example, we also have a percentile filtering on the data, so that what we do on the bottom slider is we remove the top percentiles of the distribution so that we can see the underlying distribution in the map. And then some of the needs that happen at Uber were beyond maps, and they were more related to abstract data visualization. We mentioned machine learning visualization. Who here is familiar with t-SNE? Some of you guys. So it's a way of reducing the dimensions of stuff that you pass in, and you can cluster that information, right? And so I cannot really explain what every circle here is, but you can see really interesting clusters forming from this information. And so this can also be built with WebGL and deck.gl. Finally, something that we've worked on that we're really proud of is this thing called high precision rendering for dynamic range data. So this is a challenge that happens with a lot of like geospatial type of libraries, which is that like currently WebGL only supports 32-bit floats. And that is not enough precision to go from like a worldwide type of view up to like the intersection level information. And so what we did is we worked around emulating higher precision floats, especially emulating 64-bit precision floats. This included recreating all of the math functions on the GPU to do this like packing and unpacking of vec2 of floats. And it can be proved via this very trippy video that, what the enhancement is. So basically on the left, you have 32-bit floats. On the right, you have 64-bit floats. And you get to see how much more you can actually zoom in. So if this was a map, you probably now would be seeing at somebody's toes or something. Okay, so how do we use deck.gl at Uber? As I mentioned before, the team is using it in different ways, given the nature of each one of the sub-teams of the group, and given each one of the functions. So for example, on the dashboarding side, we would be using some of the geospatial tools more for like data exposition and data presentation, right? But on the advanced analytics side, we might be using these geospatial tools more for data exploration and visual data exploration. In this case, this is one of the tools, for example, and it shows different ways of like changing, resolution onto how you aggregate data. It shows turning on and off different layers to have a different look in your information, and everything runs pretty smoothly. In terms of like volume of data, you may have hundreds of thousands of elements. So definitely, if you want to go over to like billions of points, you should definitely have some sort of like smart trick to talk to the server or some GPU database or something like that. But it's fairly responsive and has worked pretty well for us. As I mentioned before, as part of the third group that started with the ATG collaboration, we started using deck.gl for visualizing what a car sees and what a car thinks. And so this is one of the internal products that we've developed with deck.gl. In this case, we're visualizing and surfacing like over 80 layers of data, and you get to see some of the perception information from the car, some of the prediction data from the car. You can track an object, you can track the car, and essentially it works like a video game, which is very fun to develop. Cool, so now that you've seen some of the main principles of the framework, and you've seen how this could be applied to either your day-to-day job or into like maybe really complex scenarios, how does deck.gl work? And so this is the main overview of the library. It all starts with the left side, I would say, of this slide. So you have a React component, and you have some data that you want to visualize. And this gets passed into deck.gl. If you wanted to render this with a map, then on the right, you can see React Map GL, which is a friendly React wrapper around Mapbox.gl, which is what we use for the base maps. And so you can render the map with that, which is another library that you can find on GitHub. deck.gl inside contains this thing called a layer manager. And this layer manager can, manage multiple layers. You could imagine a GeoJSON layer, and as you're parsing the GeoJSON data, you can offload some computations to a point layer, offload some computations to a polygon layer, offload other computations to a path layer or a line layer. So that happens under the hood. You don't really need to know much about it. And then the purple side of things is a library that we've been developing called LumaGL. And it's our own approach to using the WebGL 2.0 API to do more advanced renderings of these objects. And so the rationale behind it is that while some libraries focus more on some of the VR and AR aspects, and they prioritize some of the new features within WebGL 2, for example, we focus more on WebGL 2 and try to use some of the capabilities of things like transform feedback to do more like GPU, like data processing. So we went with our own type of solution. Cool. So quick word about React Map GL. This is JSX code. So on the left, you get to see how do you invoke like MapGL, and then inside of you pass in like map styles the same way you would be passing in with Mapbox. But then inside of that, you can basically add whatever you want, right? So you could add a canvas object. You could add some sort of like SVG object. You could create your own scatterplot overlay, and this is where the magic of deck.gl lies. Here you could pass in deck.gl as well, and deck.gl will create all these layers for you and, be really resource efficient in terms of like using the WebGL context and stuff like that. We talked a little bit about LumaGL. So the idea behind it being a more general purpose lightweight WebGL framework. Some of the cool things, we're using a pretty modern code base for it. ES6 code base using classes that wrap actually the main concepts of WebGL2. I think that, the code base is a pretty good mapping of like, if you wanted to dive into WebGL, but you don't want to use something that's super high level, but still you want to learn the main concepts, having a read at the code base might be pretty interesting. And then it's WebGL2 ready. So we have some of the main features that we wanted to use within the visualizations that came up on WebGL2. We kind of implemented those in Luma. Cool, so those are the internals. Okay, now I want to create a layer. There are three ways in which you could visualize data. One is, as I mentioned before, we provide you with a dozen core layers, so you don't really need to worry about any of the last 10 minutes that I just mentioned. And you can just use the APIs within those layers directly. Some of those can be seen on the right. So there's like a stack rank, like, we can use our layer with S2 cells, with hexagons, grid data, icons, scatterplot, extruded choropleth, and so on. The other option, so how do you use existing layers? You go to our examples, you'll see a link that says view code. You hit there, and then you look through the code of that specific examples. The examples are tailored towards like, teaching you new concepts one by one and not really overwhelm you with really complex things. But as you're looking at the code, for example, in this example, we used the scatterplot layer. If you want to understand better like what each prop does, then you can go through the documentations, and we also have interactive documentations for those as well. In this case, we're calling the scatterplot layer within a larger deck.gl overlay class, and then the deck.gl overlay class will be included within the React Map GL instantiation, as you get to see it here. So instead of having a scatterplot overlay, we have a deck.gl overlay, and that helps you just create whatever, instantiate however, how many layers you want. Cool. The other option is to extend your layers. So maybe you want to add a functionality to a layer that doesn't exist in it, or you want to hack like into your own shaders because you're into shader programming and you'd like to customize something in that way. Extending layers is a possibility for that. This example is an interesting example for the concept. I'm not sure we actually use this because it's not super useful, but this is a scatterplot layer, and we decided to extend the scatterplot layer to add rounded rectangles. So instead of having like just circles as the points, we have rounded rectangles for it. So the things that we need to override when we subclass this are the drawing function, which is the first method there. So we're going to be passing in a corner radius prop, which isn't uniform actually, but you can think of it as a prop. And then the get shaders method, where we'll reuse a vertex shader, but then on the fragment shader, I'll go ahead and write my own fragment shader because I know GLSL code. And then on the fragment shader, what that means is that you get to see that discard keyword there. That means that I'll be like dropping pixels. Every time I'm rendering a square, I'll be dropping the pixels to make them like rounded squares, basically, based on some distance from the center. So finally, what I feel it's like the most powerful thing that you can get from deck.gl is its composite layers. So we talked really briefly about this when I mentioned the GeoJSON use case, but you can manage multiple primitives into one layer. So for example, you want to parse GeoJSON. GeoJSON has multiple like kind of geometry types. So you could delegate those geometry types to sublayers that only do one task, right? And they're like easy to test, easy to benchmark, etc. And they're reusable. So for example, if you had a point layer or a scatterplot layer, every time you get a point geometry within your GeoJSON, you can just like delegate that to your sublayer. That could be a way of creating a composite layer, a GeoJSON layer as an ensemble of 3 other layers. Composite layers could be adapter layers. Let's imagine that you're using D3 and you want to create like a Voronoi tessellation of something. So you could, create a layer that takes in sites or points and then uses D3 to create the Voronoi cells, and then uses the polygon layer to render those cells. So what you did there is you just changed the API. You just created an adapter layer. Yeah, those are the only two main reasons I can think of. So I won't go into detail for that, but I'll kind of switch over to an example I've been working on with deck.gl a few months ago. And so the main idea behind it was to create a set of custom layers to visualize wind. So one of, there are many ways to visualize wind. These are 2 layers that I've developed. One of them is more of like the traditional kind of vector field arrow type of visualization. And there you can see instancing really playing well, right? Because you have every arrow and you instance all of these arrows and you tweak it to pass in like different orientations and so on. And the other one is the particle layer. So I'll go into a little bit more detail into the process of creating this. So to start with, a long time ago, I built this example that Patricio Gonzalez Vivo, who's a creative developer now working at Facebook, and he was at Mapsen before, he kind of recycled and used the same data set to use Tangram to kind of visualize this. So that inspired me to go ahead and again, reuse that very same data set to do a remix of what he did. And something that really bothered me about this data set was the fact that you have information here encoded into every wind station, right? Which is, temperature is encoded with color, orientation is encoded with this little arrow there, and then wind speed is encoded with the radius of each circle. But this information is very localized. You have this data by weather station right now. So it's really hard and challenging to really interpolate and say, okay, what is the wind speed, temperature, and direction in some random point. And so in order to get to that data structure, a true type of vector field data structure, I started to think what was going to be the best way to do this sort of data processing. And you can use the GPU for that fairly efficiently. So one of the options is you can have each weather station and encode temperature in the red color, orientation in the blue color, and wind speed on the green color. So let's imagine that here we have 3 different stations, right? And you plot them on a map or on an image, whatever. Now, if you wanted to figure out the interpolation within these three stations, one thing that the GPU is really good at is just like rendering triangles and interpolating linearly colors within those triangles. So now we mapped data over to colors, and we're rendering colors in an image, and we leverage this sort of like GPU feature to get these sort of like linear interpolations. So this is a really fast method that lets you get this sort of like data interpolated. So I use a Delaunay triangulation to get the triangles from all of the wind stations, and then I render that onto an image, and I got all of the interpolated colors. And then what I need to do back is get back the colors from any random pixel in this image and convert those color scales that may go from 0 to 1 or 0 to 255 over to the actual like value of the wind. Hopefully everybody followed me there. So after doing that, I started thinking about, okay, how can I create a layer that shows wind through, you know, this sort of like little arrows. So it's fairly straightforward through that instancing concept that we talked about that WebGL is so good at, and that deck.gl uses a ton. So I started designing this. This is an intermediate step where I'm already powering the vector field layer based on some of the data coming from this image that now is data, this interpolated wind image. I have a layer there showing also the wind stations. And I was just for debugging plotting the Delaunay layer with elevation because I had that data as well. Working through getting some of the lighting for the surfaces. And this is the first example. So you have 72 hours of wind, so you can scroll through the slider. Every hour is interpolated, so you get to see like, you know, second or minute kind of resolution. That point there is Mount Washington, which is an extremely windy area in the US. And as a first step, I think that showing underneath it, you get to see the yellow points of each one of the wind stations on the map. So that was the first step through the project. The second step was thinking through some of the particle rendering and trying to figure out how to add more motion and dynamic to the visualization. So I won't go into details, but on how I worked on the particle layer. But one really cool thing about this is this is how things get rendered in WebGL. So this is called a rendering pipeline. You get in some points in 3D, and they go through this process called vertex shader, where you can manipulate those points. You can translate them and scale them and rotate them and so on. And then you don't get that data back. This follows this pipeline process all the way until it gets rendered through the screen. So fragment shader, you decide which pixels to discard or which pixels to keep, which is what you've seen in the code earlier. But the interesting piece is this vertex shader, right? You could pass in any data to it. It doesn't have to be 3D points. Like it can be any array of floats, and then you can perform these computations in parallel using the GPU. So why not get that data back once I perform this computation? So this is one of the key things that WebGL-2 enabled, and it makes really easy to do like data processing with it. So I use that concept with the wind layer. So based on the interpolated kind of wind map, I created this sort of like particle layer. So there's about 1 million particles. I throw them at random locations on the map, and I simulate like where they go based on some of the interpolated sampling from the wind information. I wish I had this really large screen at home, but it looks awesome. And then as you change the time, you get to kind of see how the particles adapt to that. And then you have the particles live for some time, some seconds, and then you collect them back and you throw them at some other random location. So that was the first approach to a particle layer. Cool. So that was a summary of the example. You've learned a little bit more about deck.gl. Hopefully it wasn't very intimidating. It definitely isn't, and you should check it out. You've seen some of the examples at Uber, and this is the team that has been behind all this. I'm just getting all the credit for it. Thanks.